All right, so picking up from where we left off the last video, I am again going from our last answer was 0.0049. So now, forward. Again, don't worry about the page number on there. This is for an old lab manual. So 0.0049 was our conversion answer. Now, if we wanted to write this in a way that didn't need to have all of the extra zeros, we could write it in scientific notation. So the first thing we're going to do is move the decimal to after the first non-zero digit. In this case, our first non-zero digit is 4. 1, 2, 3. All right. We put our decimal there and we add times 10 to the end. Now we count the steps that it took us to get our exponent. We had to bounce 3 times, so our answer is -3. Now the question is positive or negative. If you are dealing with a very large number, you're going to have a positive exponent. If you're dealing with a very small number, as in a number that has would be a decimal, you're going to have a negative exponent. Then you're going to drop the zeros and check to see if your answer makes sense. Now, if I look at this number, 4.9 times 10 to the -3, and I wanted to write this back out in expanded form, I could use that negative sign as a reminder that that's the direction I am going to move the decimal. So it's pointing that I need to move it to the left 3 times. And I can remember that 0.0049 is a very small number. Now, how are the base units related? I mentioned before that kilograms and liters are related. If you think about that smart water and the size of the bottle being 1 liter, but the weight of it being 1 kilogram, gives us a way to convert between things. Now, if you were to have a cube that is 1 centimeter by 1 centimeter by 1 centimeter, you multiplied those together, you would have a centimeter cubed, or a cubic centimeter. This is also shortened to be cc. So if you ever hear doctors talking about a cc of something, that is a cubic centimeter, which the volume it would take to fill it up is 1 milliliter, and the weight of that would be 1 gram. This is all if you were working with water. Some of these things would change if you had something that was a different density. But for water, we have our meters, liters, and grams. Those are the bases in there. Now, a centimeter is not a base unit. Only meter would be a base unit. Centi is a prefix. But we can now convert between volumes, weight, and volumes and length. So cubic centimeter is the same as 1 milliliter, which is the same weight as 1 gram when dealing with water. You could also say a cubic decameter is the same as 1 liter, is the same as 1 kilogram, but that's kind of weird to say. So if the doctor asks for 7 cc's of medicine, how many milliliters is that? 7 cc's is the same as 7 milliliters, which would weigh 7 grams. It's very straightforward. Cc to milliliters to grams. Now, if you wanted to convert it to kilograms, you would have to account for that 1,000. So since 7 grams would be moving the decimal over 3 times, it's not 7,000 kilograms, it's 0.007 kilograms. Now, temperature, we have, commonly in America, we use Fahrenheit, but most of the rest of the world uses Celsius. And in science, we're going to use Celsius. There are other types of science that will use Kelvin, like when you're discussing temperatures in outer space, but we are going to assume all of your experiments are being done on Earth. So rather than worrying about you learning the conversions, I typically only had students do memorize the kind of more exact numbers that you would need to know for class. So water freezing would be 32 degrees Fahrenheit, but that's only 0 degrees Celsius. Water boiling, 212 degrees Fahrenheit versus 100 degrees Celsius. So if you're noticing, everything seems to be based off of water. The weight of water, the volume of water, the point at which it freezes and boils. That's because this could be used all over the world and everybody would have a standard. The two other ones are that the human body is 98.6 degrees Fahrenheit, which is 37 degrees Celsius. A lot of times if we talk about enzymes and stuff, they'll talk about 40 degrees Celsius. That's because it's just the roundest number that is near our body temperature. And room temperature, about 70 degrees would be converted to like 21 degrees Celsius. So if we say something's 20 degrees Celsius, you can think room temperature. So other conversions to think about. I will never ask you to just memorize all of these numbers, but you do need to be familiar with them. If it is important for the math question, I will give you the information. I will tell you that 1 inch equals 2.54 centimeters. But I use the picture of the hand here. Let me see if I can. So the hand image is because I said that 1 centimeter was the width of your fingernail before. Now 1 inch would be if you were to turn your knuckle like this, that would be about 1 inch. If somebody had very large or very small hands, that would change a little, but it's just something to jog your memory. Now, I said before that kilometers are smaller than miles. So that's why if you look at on your speedometer, you're looking over here, you're going almost twice as fast. It's about 60% increase there on the kilometers per hour versus miles per hour. And for pounds, that bottle of smart water would weigh 2.21 pounds. A gallon of milk would be about the same as 2 liters. 2 liters would be 4 liters, 3.8 liters. So what about ounces? So 1 ounce is the same as 30 milliliters. And we said before that milliliters equaled grams. So it should be 30 grams, but other people say it's 28 grams. So what's going on there? And this has to do with density, how I talked before that the conversion rates were based off of liquids or were based off of water. But if you were to weigh something that is like a dried herb instead of a liquid water that would fill in all the spaces, those extra air holes would then make your product weigh less. So you have to pay attention. If you were to weigh something like mercury, that's the silver stuff that's inside thermometers, it would be much, much heavier than water. So it would weigh way more than 30 grams. We're going to do one more conversion problem to practice the math here. So Jimmy is walking through the airport with 27 kilos, that's kilograms, of cocaine in his bag. The ticket agent says his bag is too heavy. He must pay $5 for every pound over 50 pounds. How much would he need to pay? So we know from the question before, or from the information we were given before, that 1 pound, or that 1 kilogram is equal to 2.21 pounds. Give me a whiteboard. Okay, so 1 kilogram is equal to 2.21 lbs. That's the shorthand for pounds. So if we had this and we want to multiply each side by 27, give you another color, we would say 27 times that 1 kilogram would be equal to 27 times that 2.21 pounds. Pulling up the math here for you. 27 times 2.21 is equal to 59.67 pounds. Okay, so, but the question said, how much would he need to pay? And he got the first 50 pounds free. So we need to now subtract 50 pounds, minus 50. And we're going to get our answer is 9.67 pounds. And we're going to assume he's flying American, and they're going to round that up to 10 pounds. So we're going to say 10 pounds times $5 is going to equal $50. Now, is it worth it for Jimmy to put this bag on the plane? And we can probably say that depending on the market value, oh, don't go backwards. Going back to my screen. That yes, Jimmy's going to attempt to load the bag on the plane. Jimmy is arrested and learns the top level punishment for cocaine is over 400 grams. Will he be charged with this level or a lesser crime? So going back to my whiteboard, I said before that the acronym that I use is King Henry died by drinking chocolate milk. Let's space those out a little bit better for us to be able to see. And if you wanted to keep going, don't forget you have to account for those extra spaces. And I believe micro is the mu symbol. That's a kind of like a weird swirly M, but you can show it as a U. Micro, nano, pico. Okay. So now we want to know, is 27 kilograms kg is equal to how many grams? So we want to convert. We know we are going from kilo, okay, down to the base unit of just grams. To get from there, we have to go 1, 2, 3 decimal places. So we take our 27 and we're going to move 1, 2, 3 decimal places and replace it. Put in our zeros. And we can see that 27 kilograms is equal to 27,000 grams. Well, that's not so good for Jimmy. What's going to happen? Oh, Jimmy's going to go to jail. Womp womp. Okay, so laboratory equipment, there are a couple different videos about these items, and I hopefully will be able to upload a document that has them all kind of compared side by side, you really should just know that a graduated cylinder, tell you what, we can do it this way. Is a very tall, thin measuring device. The graduated part means that there are gradations on the size to determine the measurements. These are accurate for measuring liquid substances. When you go to read it, you need to move down to eye level, and it has this curve shape to it based on the surface tension of the water. This meniscus that is formed is made to be read at the bottom of the curve. So if you look down at eye level, and wherever the curve dips the lowest, that is the measurement. So in this case, if this is 30, that's 40, that would have been 35. Our answer is 31, 32 in this case. Now, by comparison, we can see this picture here. This is a beaker, not a graduated cylinder. So beakers are shorter and fatter. Yes, also a Muppet. But shorter, fatter, these are not accurate for measuring. The numbers on the side, if you can see here, are just very approximate. It even says approximation on there. They don't worry about being detailed. It's just to give you a guess. An Erlenmeyer flask. That's the next one. Erlenmeyer flask. Are this kind of thing. Now, if you were going to be mixing a bunch of stuff together and needed it to have an open mouth, you would use the beaker while you were heating it. But sometimes when you're mixing solutions, you want it to have a more narrow mouth so that the liquids don't evaporate, and that's where you use the Erlenmeyer flask. Again, these are not accurate for measurements. You can see it just has really close approximations on it. I mean, like really spread out numbers. This one says plus or minus 5%. You don't want to be off by 5% in chemistry or biology. Part of the other PowerPoint has a video link for using the triple beam balance and the digital balance. So I'm not going to go over those at this point. The weighboat should also be discussed with that. And you don't really need to worry about a stir plate or hot plate because you aren't going to be working in the lab. The graduated pipette, however, might come up on some questions just because it'll assume you know what it is. So a graduated pipette is usually a very, very long, thin measuring device. These are accurate. So this would be like when you need to measure like less than 10 milliliters, this is what you would use instead. It would also form the meniscus, and you could know how accurate you were being. In order to use it, you have to suck the liquid up. You either use a bulb like this, or it attaches into a plastic thing with a roller. Again, since we are not going to be working with these in person, it's not so important that you know how to use them. But eyedroppers work on the same idea, that you're sucking the liquid up and then expelling it out. And as before, you have to read the bottom of the curve. Okay, that's the end of today's lesson.